Okay, in the previous video, we constructed a power series for e to the 2x. So we used the idea that we could substitute the 2x into the summation. Well, with that idea in mind, let's now generate a series for e to the I theta. Let's generate a series for e to the I theta. We're going to use the same idea. And something really interesting is going to happen. And we're going to end up with a result that is one of the most beautiful results in mathematics. So e to the I theta, that means we would go into our e series, which is the sum, as k goes from 0 to infinity, of the expression to the kth power, so I theta to the k, all that over k factorial. And let's start working out the first few terms, and then we want to notice something about these terms. So on the one hand, k equals 0, right? Anything to the 0 power is still just 1, right? As long as that stuff's not 0. And then over 0 factorial would still just be 1. And then k equals 1. You'd have I theta to the first power over 1 factorial. So we would just have I theta. K equals 2. We would have I squared, which we know is negative 1 times theta squared all over 2 factorial. So this would actually be minus theta squared over 2 factorial. I'm going to keep it as a 2 factorial there rather than writing 2 because I want to look back at this later. Then we keep going. K equals 3. Well, then we're going to be dealing with I to the third. I to the third is negative I. And then that'll be theta to the third over 3 factorial. So this is going to be minus I times theta to the third over 3 factorial. And then we're going to keep going for a few more terms. And again, just for your reference and just to recall, I to the 0 is 1. I squared, I to the first, of course, is I. I squared is negative 1. And I cubed is negative I. So when we get back here now for k equals 4, we'd be back to I to the fourth. But I to the fourth is the same as I to the 0, which is 1. So this would be plus theta to the fourth over 4 factorial. And we get up to k equals 5. I to the fifth would be the same as I to the first. So we're going to have an I and then theta to the fifth over 5 factorial. And then just a couple more here. K equals 6. I to the sixth will be the same as I squared, so it's going to be minus. And then we would have theta to the sixth over 6 factorial. And then keep going one more here. I equals k equals 7. I to the seventh would be the same as I to the third, so it's going to be minus I. And then we would have a theta to the seventh over 7 factorial. And so on, repeating over and over. So you're going to have 2 positive terms, then 2 negative terms, 2 positive terms, right, and then 2 negative terms. And it's going to keep going like that. And notice that I shows up in half of them, and in the other half it's not there. Okay. But hold on, a little bit more here. Let's make these terms kind of stand out a little bit more here. Okay. Let's make these terms stand out just a little bit more here. So the purple ones there, I could write this down as a group. right? Because, right, we can regroup stuff, right? So I'm going to group all the purple ones together. So we have 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial. And the next one will be plus, and so on. And then our second group here, the second group, they all have thetas with them, or they all have i's with them. So what I can do with that group is factor out the I, since it's in every one of them. So I can say we have that stuff plus that, and then plus I times theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial plus, and so on as well. So we can write this as a sum. We can write this as a sum. And when we do, I'm hoping it might be a little familiar here. Hoping that the sum might be a little familiar. All right, this would be the sum as k goes from 0 to infinity of theta raised to the 2k power over 2k factorial, and then we got to deal with the alternating sign. So 0 is okay, the next one is not, the next one's positive, that would be k equals 2. So we would put a minus 1 to the k out front. I'm just going to slide that over a little bit, and we would have a minus 1 to the k times that stuff. That should look pretty familiar to you. That should look pretty familiar to you. If it doesn't, let me help you out here. We developed the Maclaurin series for cosine and found out it was exactly that thing. So what we actually have here is the terms that don't involve I in the expansion of e to the I theta are actually just our cosine series. So this is actually just cosine of theta. Okay, what about the second half here? So there's the purple stuff. Purple stuff is all just, in the end, the infinite series of the cosine. What about this other stuff? Well, we could also collect all of those and realize we have theta. And once again, we have alternating signs. So we have the I sticking out front. So we'd have the series as k goes from 0 to infinity, and we have alternating signs. Again, so minus 1 to the k. And then we're going to have theta is raised now to odd powers. Remember, if it starts at 0, the odd powers would be to the 2k plus 1, and of course that's the same thing for the denominator, 2k plus 1 factorial. And I'm hoping that piece will look a little familiar to you. If it doesn't, we've also seen that one recently. Let's just scroll up a little bit. When we differentiated our cosine series, right? We differentiated our cosine series. We got exactly that series. Right there, k equals 0 to infinity of minus 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. And so therefore, we have this amazing result. This amazing result that e to the I theta is equal to the cosine of theta plus I sine of theta. Okay, this beautiful, beautiful result. A famous mathematician named Richard Feynman referred to this equation as our Joel, right? The most remarkable formula in mathematics. And so this is this thing that allows us to convert from a complex exponential function over to an expression involving our trig functions sine and cosine. So it is quite a interesting result. Now, very important here, all of this stuff involved derivatives, power series and stuff, involved the derivatives originally of the sine and cosine. Remember, those were all based from a calculus point of view, where theta here is in radians. Okay, anytime we do anything in calculus, theta is pretty much forced to be in radians. So this thing is known as Euler's formula, after an individual known as Leonhard Euler. And a very special case of this formula is this. If we let theta be equal to pi, then we get e to the I pi is equal to cosine pi plus I sine pi. But sine of pi is 0, cosine of pi is -1. So we get this formula, e to the I pi equals -1. But with a quick little manipulation, we get this very famous formula that connects the 5 most important constants in mathematics together. E, I, pi, 1, and 0, all in the same equation. Okay, so this is quite a remarkable result, and we're able to get it from our power series. This is quite a neat result that we get off of power series.